All right, ladies and gentlemen, class recording for today has started. So, over the past couple of days, we have been discussing the relationships between four different things that we use to describe motion. And what are the four features that we use to describe motion that we've been talking about and how they're related to one another? Four key vocab terms from this unit. Acceleration is one of those terms. Velocity is another one. What's another one? Speed, kind of, and velocity are sort of related to each other. So acceleration, velocity, and two more. Displacement, and then there's one other factor that entering into all of this, time, right? So we've been looking at how those four things all are interconnected, and if we change one, we cause changes in the other one. So we started our discussion with constant velocity, where nothing is changing. The displacement each second stays the same, the velocity stays the same, the acceleration is 0. And then we spent a lot of Tuesday and yesterday talking about constant acceleration, where something is continuously changing velocity. And we looked at a couple of times when this object was rolling down the hill. Based on the acceleration value, we can figure out what are the instantaneous velocities. And from those instantaneous velocities, the displacement during each time interval. Okay? Good there? Yesterday, at the end of class, I gave you this ramp. Right? We didn't quite get all the way through it, so let's figure this out here, then we'll move on to the next stuff for today. All right? So, said this ramp was an object as it rolled down this ramp, was it experiencing an acceleration of 5 meters per second squared? And we said that 5 meters per second squared is the equivalent of 5 meters per second, right? And so, starting up at the top, at t equals 0, the instantaneous velocity is 0. Right when we let that ball go, it's not doing anything. But immediately after that, it starts accelerating, and velocity starts changing. In this case, what type of acceleration is it experiencing? Positive acceleration is going to speed up and speed up and speed up. Okay? And we could go through and fill in all these individual or instantaneous velocities, but because the acceleration is 5, this one would be 5, this would be 10, 15, 20, 25. Okay? 25 being the instantaneous velocity at the very, very end of the ramp. Good there. Okay. Right at the end of class, I told you that the average velocity was 12.5 meters per second. There's two ways we can figure that out. First, if we just look at the beginning and the end, right? We said averages. We add everything up and divide by the number of things that we added. If we just look at the beginning and the end, 0 at the beginning, 25 at the end, 0 plus 25 is 25, divide by 2, because we're only using 2 velocities, that gives us 12.5. The other way we could do it, knowing all of these instantaneous velocities, we could add up everything along the ramp. 0 plus 5 plus 10 plus 15 plus 20 plus 25. We got to include the 0 in there, because that was one of the instantaneous velocities that we talked about. Right? Adding all of those up and then dividing by 6, because we have that 0 value there, guess what you'll get? 12.5. Okay? So that's the average velocity of this object as it rolls down the ramp. Good there. Now, that's not what we ultimately wanted to find out, right? My ultimate question to you was, how long is this ramp? Right? To figure that out, we're going to use the same relationship that we've been using to describe velocity, right? velocity, regardless of how far or how long or whatever it is a relationship between displacement and time. We just calculated that the average velocity of this object on the entire ramp was what? 12.5. So we'll plug in 12.5 for the velocity. We don't know how long the ramp is. That's what we're trying to find out. And now we include a time. Here, when we were calculating all of these individual displacements from each interval, the time was always what? 1 second, because each one of these intervals represented 1 second worth of time. Here, though, how much time are we talking about if we're relating it to the entire ramp? 5 seconds. So here, if we want to know the distance of the entire ramp, we can plug in 5 for that time. Velocity is still a relationship between displacement and time, but now we're just looking at it over a longer period of time. Does that make sense? And so now we solve for question mark, right? Hopefully it's not too difficult for you, and you should find out that this ramp is 62.5 meters long. Does that make sense? Same procedure, just now we're looking at it over a more extended period of time, which is fine. We just have to make sure we plug in the right time frame into that velocity equation. Good there. You okay with that? Okay. Before we pick up the packet in the next section there, I'm going to do a couple of demonstrations up here in the front of the room. And we're going to talk about some ideas, which is actually a pretty good review for the test. So we'll start doing that, okay? All right. First, have any of you ever used the Vernier LabQuest before? If you took pre-engineering last year at Mr. Thoning's, you might have done a little bit of it. Some science teachers do, not a lot of them. But anyway, if you have not used it before, this is what it looks like. Okay, it's a representation of it up here on the board. Okay, basically it's a computer, and we can hook up different electronic measuring devices to the computer, and it will record measurements much faster than we can record them as people. Okay. Right now, I have attached to it this green box that is the motion detector. So if you're sitting close, or maybe even if you're not sitting close, you can tell that it's clicking, okay? Making little clicking noises. So what it's doing is it's making sound waves. And those sound waves are going out into the room, bouncing off of stuff, and coming back to the motion detector. And depending on how long those sound waves are gone, it can tell how far apart things are, or where things are. It's very much like echolocation in a bat and stuff like that. Okay? So, or what?
We watched a video in class about some guy that flew flying.
Oh, yes, yes. So here, I laid it down on the table. It's pointing at the ceiling. The ceiling is 1.944 meters away from the table. So they can tell how far. It can tell how long the sound waves have been gone, how long it takes them to get back, and it measures distance that way. Okay? Good there? All right. So here's what we're going to use it for today. I am going to take this volleyball, and I am going to toss it into the air, just not real far, like this, right above the motion detector, and it's going to record the motion of that volleyball, and we're going to look at a couple of graphs and analyze those graphs. Okay? So first, I'll zoom it in here so that you guys can see the graphs more clearly. There we go. All right, so first, I did this earlier today, and I got like 2 perfect graphs. So hopefully I will get a perfect graph for you guys to analyze. If not, we'll just have to use my data from earlier this morning. So. Okay, so let me do this, and we'll go from there. Okay, 2 graphs up on the board, right? Let me change one thing about that graph. about one of the graphs? No, I'm just scaling it. Alright, so here's my two graphs. Okay? Let's take a look at the top one first. Position graph. Okay? What does position tell us? Where it is, right? Relative to what? The reference point. Jack, what's the reference point in this experiment? The lab quest, or the motion detector that was measuring, okay? Because did I start at zero position? Does the position graph start at zero position? It doesn't. The lab quest is the reference point in this problem, okay? Reference point is the table, or the lab quest, or the motion detectors. And then we have to do directions, right? So the way that the lab quest is facing, up is positive, down is negative, okay? Do we see any position values that go below the x-axis? Here's the x-axis, right? This thicker black one, right? For this one, sorry. Position values. Let's stay up here for now. Position values. Are any position values below the x-axis? If they would, what would that represent? Where would the volleyball have to go? Under the table, and it doesn't go there, right? It can't. The motion detector can't measure that anyway, so we don't see any negative position values. All right. So position graph starts off horizontally, right at the very, very beginning. It's a horizontal line. Why? When it started measuring, what was I doing with the volleyball? Wasn't moving. What's the first thing that happens in the position graph? It dips, right? It goes down. That means it's getting closer to what? The sensor, because what's the first thing I did? I had to drop it down, then to throw it, right? Then we see the object flying through the air. What shape is the position graph? It's a parabola. What is that telling you about the motion of the volleyball? It's going up and then down. What's happening to it as it's going up and down? What about it is changing? Yes, its position, something else. Direction changed as well. There's one other thing. Its velocity changed. Why, Fiona, do you know that? Is the slope of the position graph constant? It's a curved line, right? It's a curved graph, and curved graphs represent changing velocities. Okay? Good there? All right. Let's spend most of our time talking about the velocity graph. So I'm going to do here, and I'm only going to show you the velocity graph here. Okay? All right. Where does the velocity graph start? Starts at zero, because what was I doing with the volleyball when I was holding it still? First thing that happens to the velocity graph, it dips down, representing what kind of a velocity? A negative velocity, because what's the first motion that the volleyball did? Down. Then I throw it in the air. So during this section right here, what's happening to the velocity? It's positively what? Increasing. Okay? What's the first thing that happens to the volleyball? I dip it down, but then what do? I throw it in the upwards direction. My hands make it go faster in the upward direction. And that happens until we get here, right? What happens to the velocity graph after that point? Not quite yet. First, what does it have to do? It's decreasing velocity because the velocity is getting closer and closer and closer to what?
The reference point.
On this graph, does that represent the reference point? No. Because remember, this graph isn't telling you where, it's telling you what. So during this section of the graph, right here, what's happening to the velocity during that section of the graph? It's decreasing, but it's still moving which way? It's still moving in the positive direction. And we discussed here, what is the positive direction in this lab? Up. So that's the point. So what happens right here? What happened at that point right there? The velocity, well, it did change, but it's been changing the whole time, right? It's been going up, but now it's increasing, but after that point it starts what?
Decelerating.
Let's go with the velocity is,
Accelerating slower.
let's go decreasing, okay? What causes the volleyball to slow down?
Gravity, air resistance.
Let's go with gravity, more so than air resistance. Air resistance does play a small role, but gravity's playing a bigger role in this game. So, gravity causes it to slow down, right? So what significant event in our lab occurred at that point on the graph? Gravity started doing what? Making it do what?
Go down.
Not go down,
Slow down.
slow down. It's still going which way? It's still going up. When does gravity start slowing it down as it's traveling upwards? As soon as I stop doing what? As soon as I stop pushing it. That spot on the graph is the moment it leaves my hand. Because at that point, it goes from speeding up because of my hands to slowing down because of gravity. Does that make sense? Okay. What happens right there? Fiona, go ahead. So that's the top of the motion, right? Okay, so it starts coming downward. What does it have to do first before it starts coming downward?
Stop.
Has to stop. Is it stopped for very long? No. There is a moment when it has an instantaneous velocity of 0, but it doesn't last very long. Okay? Good there? All right. Here's the trickier part. What happens after that point? Sophia, go ahead. It speeds up, but going which way? Downward, in the negative direction. Right? This section from here to here, even though the line is sloping downward, represents the object speeding up. Okay? Why? Because what's happening to those velocity values? They're increasing in the negative direction. -2 is faster than -1. -3 is faster than -2. Does that make sense? Right? So even though that line is going downward, it's speeding up once it gets past the x-axis. Okay? Ultimately, what happens to the velocity graph? It ends up back where? It ends up back at 0, right? Because what is this section right through here? What is that section there that I have the arrow over? What is it doing there? It's slowing down because of what? My hands. That's when I catch it, right? Even though the line is going upward, it's still slowing down. Hey. Say again. Put it right there on that table right there, if you would, please. Thank you. All right. Are we good with this graph? Are we good with interpreting this graph? Okay. So, question. We're going to spend a lot of time talking about this section through this section. Okay, that section that's highlighted there. What does that section of the graph represent? The ball going up and coming back down, right? What's causing it to go up and come back down?
Hands and gravity.
No, not hands anymore, right? We said hands stop right here. So if I highlight from here to here, I'm only focusing on what?
Gravity.
Gravity. Does gravity cause an acceleration? Yes. What's happening to the velocity during this section that I have highlighted? Is it changing? Absolutely. What do you see about that change? It is a constant change. It continuously gets slower and slower and slower and slower and slower until it hits the x-axis. Then it continuously gets faster and faster and faster and faster. What do we call a continuous change in velocity? What kind of acceleration? Constant acceleration. Gravity causes constant acceleration. Go ahead, Fiona. Yeah, that's where we're going. That's where we're going with this. Okay. All right. So I'm going to do this. Analyze curve fit velocity. So see, I've just highlighted this little section of the graph between these two brackets. Okay. I am going to put a best fit line in there, just like that. Okay. So it's a linear graph, right? What's the slope of this graph? You sure? 9.48. 9.48. All right. So 9.49. 9.49. All right. So the slope on a velocity graph tells us acceleration. So the acceleration that this volleyball experiences has a magnitude of 9.49 meters per second squared. The velocity changes by 9.49 meters per second for every second that goes by. But it's negative. Does that mean the ball was continuously slowing down? No. What's causing this acceleration? Gravity. What does the negative sign tell us on vector quantities? It represents what in general? Well, it represents direction, right? And which way is gravity always pulling? Downward. It just so happens that based on this positive and negative, that's the negative direction. So while I told you at the beginning, generally speaking, negative acceleration is things slowing down, that's not always the case. It depends on which way it's moving and which way it's pulling. Okay? Good with that so far? All right. This is an important concept, and we'll pick it up with the picture of this rock falling down this well, which you have in your packet. Okay? Is this rock accelerating as it's falling down this well? Yes. Yes. 2 ways you can tell me that. What are 2 ways that you can tell me? Sophia, what's one way? The intervals are not evenly spaced, right? What's another way that you can show me that this rock is accelerating as it falls down the well? Go ahead, Fiona. Yeah, you got to give me data to support that claim. If you look at the velocity values, the instantaneous velocity keeps going up, right? So that means the velocity is changing. It's accelerating. More specifically, what is the acceleration of this object as it is falling down the well? Rises. 9.8. Do you have data to support that, or do you just know that gravity causes an acceleration of 9.8? No. Okay. So, here. Okay, so you just read it off of your sheet.
No,
Oh, okay. So, if we look from here to here, right? How much does the velocity change? It goes from 0 to 9.8. It changes by 9.8. How long does that take? 1 second. If we look at the next interval, it goes up from 9.8 to 19.6. How much of a jump is that? 9.8. How long does it take? 1 second. So this acceleration represented by this rock falling down the hill, the velocity is changing by this much in this amount of time. Right? So that acceleration is 9.8 meters per second squared. 9.8 meters per second. Good? That's an important value to us because here on Earth, gravity causes a constant acceleration of 9.81 meters per second squared. The picture says 9.8. I said 9.81. It just depends on what book you read, how we round it and stuff like that. Okay? This value is so important to what happens here on Earth that we give it its own designation. We call it lowercase g. So anytime little g shows up in an equation or in a description, we are referring to the acceleration caused by gravity here on Earth. Okay? Alexa, go ahead.
So 9.1.
Yes. Yeah. So we're going to start doing some problems, and whenever you see G, we're just going to plug this number right in there for it. Okay? All right, good there? Now, going back to our LabQuest picture of the volleyball moving up and down. The slope on the velocity graph here is 9.49. It's not 9.8. Why? Was gravity not affecting that volleyball?
Air resistance.
Gravity wasn't the only thing affecting that volleyball, right? That 9.81 value applies when gravity is the only thing acting on the object. Meaning, here on Earth, it's pretty hard for us to measure the acceleration of an object as 9.81 because in most cases, gravity isn't the only thing affecting a falling object. We have to deal with air resistance and stuff like that. All right? Sophia, do you have a question? Or are you good? Okay. If we can get to the point where gravity is the only thing affecting the object, we refer to that object as being in free fall, or we refer to it as being weightless. Okay? Good there? All right. Let's watch a short little video that